two types of information. One is specific for this system, which, if we are talking about some metal, for example, then there is the shape of the Fermi surface, lots of small details, what are the impurities, and so on. And there is a quite respectable part of science which studies these specific things. But there is also another type of information which I call universal, or which can be viewed as topologically invariant, which basically there are certain formula which don't change under small deformation of the system. And the critical phenomena and more general things belong to this type of to this type of information. You can put it differently by saying that we actually have two types of modes, two types of eigenstates in complicated system. One is some highly excited levels with the energy differences defined by, say, Fermi energy or something like that, and they're really sensitive to the fine structure of the system. But there are also low energy modes, which are kind of universal. And what the Landau free energy describes is just, it was a simple example of low energy modes. There are many other examples, and sometimes it's convenient to introduce this low, so you can view the Landau free energy as low energy effective action for these soft modes. Sometimes you can describe it by the local effective action, sometimes not, but in all cases it's just the appearance of these soft modes which that leads to universality. I'll give you another example. A simplest example would be from the 19th century. I'll give you an example from 19th century and from 21st century. Simplest example from the 19th century is hydrodynamics, because we know that we have more gases composed of molecules, they have complicated interactions and so on. However, if we look at the motions which are much softer, much larger wavelength than interatomic distance, they are described universally. They are described by some coarse-grained velocity, and this velocity satisfies well-defined equations in which we keep the minimal. We once again, it's just as with the Landau free energy, we keep the least number of derivatives and write down expressions which have symmetries of our system. Now, that leads to the Navier-Stokes equation, for example. And there are good news and bad news about the Navier-Stokes equation. Everything is the good news is that we managed to get extremely valuable information about this coarse-grained velocity. Our airplanes and automobiles, they are designed using this equation. That's the good news. The bad news is has the same source as the good one, as often happens, which is that studying hydrodynamics, we will never learn anything about intermolecular interaction. So what I want to stress is that this yeah, by the way, so what I wanted to stress is that we are always dealing with long-range order with coarse graining, and it has different names in different situations, but they are intrinsically the same. So when I just wanted to stress that so that you understand that the philosophically Landau free energy is the same thing as the Lagrangian for the Euler equation or the effective action for the Navier-Stokes and so on. And when you talk about some modern things like quantum Hall effects or topological insulators, it's the same philosophy. The only thing is that the structure of these soft modes is different. Of course, it's different with different symmetries and so on. But generally, we just look. We're doing things in two steps. We look at the low energy effective action or Landau free energy. This is, as I tried to explain, kind of a synonyms. And then we decide whether it's applicable approximation. Whether, for example, in hydrodynamics, we derive this, we write down the least number of derivatives, but there are also thermal fluctuations of velocity. Are they relevant? Do they destroy the zeroth order equation? That's a question, and the answer you have to check. Just like we did in the simplest case of a magnet, we checked that we have critical dimension 4, and beyond this critical dimension, above this critical dimension, we can use the naive expression for the Landau free energy, or so you have these soft modes, and you can neglect their interaction. What I'm talking about is the interaction of the soft modes. We can use classical because of their quantum or thermal fluctuations. And you can easily make an estimate. We will be doing such estimates later, which show that, say, in 3 dimensions, hydrodynamics is fine. However, for example, there are a simplest example when it's not fine is the case when you have, say, a system with impurities. And in this system in impurities, if you approach things, if you have a particle traveling through these random impurities, it satisfies the diffusion equation, which is just a special one of the hydrodynamics equation, the diffusion equation. Now, and so the low energy mode is this, sometimes called diffusion, the slowly varying density which changes in time according to the diffusion equation. Nice. However, in 2 dimensions, it is wrong, because this diffusion is just as we saw that below critical dimension in the magnet we have large correction, which we have to account for. In diffusion equation, it's practically destroyed by fluctuations, and what happens is called Anderson's localization, when those particles are localized near some center and don't diffuse with time far away. So that's the example and in all cases when we use soft mode approximation, we have to check, we have to apply the check whether we have some nonlinear equation for the soft modes, but now include the fluctuations and see whether these classical equations make sense. Sometimes they do, sometimes they don't. Okay, that's just to remind you our general strategy and general attitude, which I think is reasonable towards. By the way, from the point of view of this attitude, the standard model of elementary particles is also the low energy Lagrangian, and we know that it is correct. It's just the marginal case for dimensions, and there are logarithmic corrections to various quantities. So you cannot describe, for example, the Young-Mills theory classically. You have to account for fluctuations and so on. Again, it's the same category of things. There is no difference of principle. It's just different system and different modes, but your strategy is the same. Okay, but then there is another approach. But then we have to face the complicated problem of describing the system when the fluctuations interact strongly, when the classical equations don't make sense, cases, so to say, below critical dimensions. And I started the discussion last time. I'm still actually in the process of reminding you what we did and maybe giving slightly different perspective, but basically we already discussed this. We said let's look at the Ising model as a model with particular symmetry, and let's try to extract some universal information. We already know that in this case it will be strongly interacting case because we estimated critical dimension and it was 4. If we are in 2 dimensions or in 3 dimensions, the system is strongly fluctuating. So we still, this is the generalized, so to say, Landau theory, in the sense that we still concentrate on the soft modes, but we don't treat them classically. When I say classically, I mean you simply minimize, you take free energy functional and you minimize it and look at the classical solution to calculate various physical quantities. By the way, from the point of view of Feynman diagrams, what does it mean to restrict yourself to the classical solution, to the classical? Yeah, it is. You can. We are basically discussing the following thing: when you have some phi to the 4 in free energy, or something else, then you have, and you're calculating, say, phi in magnetic field. The Feynman diagrams, you have to solve the equation like that. And the Feynman diagrams are something like that. There are tree diagrams, no loops, and fluctuations. So we can say that in the cases, if dimension is greater than 4, then tree diagrams dominate. If it's less than 4, then there are all kind of loops which should be accounted for. Now, so this equation for the magnet is nonlinear, and indeed it is. I also said this already, that if we use the representation for the Ising model where the potential energy is log cosh phi, we see that the drops of minus spins, when they touch, we need to correct this because of the interaction to get the correct counting. When the two drops touch, we should get the coefficient 1, and as I explained, naively, without it, you would get the coefficient 3, because there are 3 diagrams like that with the different. And in any case, it looks pretty hopeless in this approach, because although we understand very well the origin of this log cosh, as I said, you can check in some more complicated diagrams that it always takes care of the right counting of the diagrams. We don't know how to solve it. It's nonlinear equations and nonlinear quantum equations. Hard to solve. And what I said last time, that there is another type of quantities. There is a very tricky and unexpected change of variables when you introduce the disorder parameter. Again, I remind you the disorder parameter is defined on the dual lattice, and it is a point with a tail or with a string attached. This string, though, is almost invisible, in the sense that, so the definition was that whenever the link is crossed by this invisible string, you change the sign of the interaction. So if these are 2 points, 1 and 2, since the link is crossed, if we place it here, the link is crossed, and we get, we have to add e to the minus 2 beta sigma 1 sigma 2 to the partition function. All the rest is the same, and here we have to add e to the minus 2 beta and so on. And the correlation function is defined as a ratio. Now, the wonderful thing about this, there are many interesting things about this disorder parameter, but the most interesting thing is that the product of order and disorder. So we took disorder. We took some side of the lattice. We have 4 vectors here, and we have 4 vectors here. Okay, and we define the fermion as sigma of x at the point x as sigma of x mu of x plus EA. It is the product of order and disorder. It is not possible to express it in some local way while sigma is trivially related to the field phi. Mu is not. It's a very indirect change of variables. However, what is remarkable about this thing, for example, let's take this is 1, this is 1, 2, 3, and 4, is that you immediately derive the equation, the linear equation for this fermion on the lattice. And we do this by simply, in a very trivial way. There's absolutely straightforward. You just write it down as cosh 2 beta plus sigma 1 minus sigma 1 sigma 2 sinh 2 beta and see what's happening. If we use this formula, the term with sigma 1, sigma 2 will cancel the contribution of this link, and as a result you will get psi at the different position. I shall, as I said, it's better to now the most that's the linear equation which follows from there, and it actually has its analogues in higher dimensions. Very interesting. It's still an unsolved problem. I mean, not 2 dimensions are of course completely solved, but 3 dimensions is still an unsolved problem. And there are interesting also other models in 2 dimensions. They could be also tricky. But 3 dimensions is of course the most interesting thing. And 4 dimensions also. But for that we need first to analyze this. The most important thing which we learned last time is that if we go from 1 to 2 to 3 to 4, we don't return because the tail twists, this invisible string twists around the spin. You get the condition that psi a plus 4 is psi a. Now, and that happened, this minus is extremely important. It happens because this invisible string attached to the dual point, it is actually not completely it's invisible for disorders, but there are seers who can view this apparition. You see, so if we have a spin, the order parameter here, if the order parameter can see it interacts with this invisible string, unlike. So, in other words, if you have correlation functions of disorders, then it's defined the configuration of tail of strings is completely irrelevant. But when you have 2 of them, you get fermionic structure. And as I shall explain very quickly, we have to actually speed up a little bit. What we get is Majorana fermions here, satisfying the Dirac equation. And I started to explain the way to get it, of course, to get differential equation from the lattice equation, is to expand, to assume that those fields change very slowly, and replace finite differences by finite derivatives. But there is one, I will not go into this, it's straightforward, but I shall explain one important point about these matters, and then we will proceed to the solution. The point is, let's suppose that we have some field phi of x, and as I said last time, let's consider transformations, say rotations. It could be field in space or it could be field on a sphere, and the rotation is given by this formula where G is the orthogonal matrix, and we always have a representation which is simply all definition to check that its representation is trivial, because it simply means that Tg1, Tg2 should be equal to Tg1, G2, which is obviously satisfied. And all other simple axioms are obviously satisfied. However, this representation is reducible, highly reducible, and say because it's infinite dimensional in the first place. And what's the dimension? Suppose you have a sphere. What would be the dimension of a reducible representation? Imagine field on a sphere, so everything is. How would you treat such a field? Let me help you a little with terminology that we already discussed the following thing, that if we have a tensor which transforms just like g I prime, g k k prime, phi I prime k prime. When we have this tensor, then it's clearly reducible. That you know very well. It's clearly reducible because we can, first of all, we can take symmetric part and subtract. We can either take anti-symmetric part, it will be reducible. We can take symmetric part and subtract the trace. So in order to get irreducible representation, we have to impose invariant constraint on this field. So, for instance, we impose the constraint that trace is 0, and and that the tensor is symmetric. That gives us irreducible representation. You cannot find any combination, any smaller combination of components which will be invariant. So we have to, the moral here is that you have to impose maximal number of invariant constraints. So you just think what are invariant constraints, and then, yes?
But why, this number is equal to 1?
Which one?
Like number of constraints, like...
it's not equal to 1. For example, if you have a general tensor, one possible system of constraints is this one and this one. So you have one constraint here and certain number of constraints here.
Yeah, but last time you said that we can introduce a Klein-Gardon.
Yeah, I'm coming to this, exactly. Yeah, I'm coming to this. I just, before coming to infinite dimensional case, Klein-Gardon, I just want to remind you something which you know very well, that you have. So, as you said, we have to. It doesn't have to be 1. We don't know a priori what it is. We just have to try our best in constraining the field as strongly as possible. And the strongest constrained field, so the constraint must respect the symmetry, and the strongest constraint leads to irreducible representation. In a sense, it is a definition of irreducible representation. So now, when we have a field on a sphere, then what kind of invariant constraint we can impose on it without? Yes, but we can impose the constraint, not simply the Laplacian, but we can impose the, so to say, Klein-Gordon constraint on it for some lambda. And it is obvious that this is the invariant. So in other words, I'm imposing the, like with Landau energy, I'm taking the least number of derivatives. So I'm imposing the constraint, the most general constraint with the minimal number of derivatives. In principle, you must take higher number of derivatives. But why I'm not doing this?
Because this would give us spherical harmonics.
This actually, if I take Laplacian square, it will not give me anything new. If I already satisfy this thing, then then that's it. There's nothing else you can construct. But now you see that the solution of this equation is just spherical harmonics. So what the conclusion, we know that the lambda for phi to be non-singular, lambda is LL plus 1, and phi is just a spherical function. And when you rotate, we have 2L plus 1 dimensional representation. So that's something you know. I'm just putting it in a slightly different way. So you just, which we will actually need this way of discussing ADS, CFT, and things like that. You have to impose the Laplacian. You have to. You can read. Let me start again. Different eigenvalues of the Laplacian form invariant subspaces of the whole space. Under rotation, if you have a given eigenvalue of the Laplacian, under rotation, the wave function will transform into the wave function of the same eigenvalue. And YLM will be transforming linearly with different m. So you have under rotation, there will be some coefficient. The important thing is that L is the same here and here. That's just a reminder, but I need one more reminder. Let's now look at the vector field. With the vector field, it's somewhat less trivial. This, by the way, is called the regular representation, and then using the Laplacian, we decompose it into irreducibles. Again, you check yourself. Well, there is nothing to check. That higher derivatives constraint don't change anything. They are trivially the same. Okay, now one more thing which we will need. And what happens when you have a vector field, AI of x? On a sphere, or in flats, that doesn't really matter. How it transforms. And clearly, the transformation law which you should use so that it's easy to remember, because if you have an invariant condition AI xi, then on this TG should act trivially, and it does. So this is the definition of the transformation. And once again, we can have the Laplacian equal to 0. But now you can see that this is insufficient constraint. It's because, I'm sorry, excuse me, it's lambda AI. Now, how would you look at this formula and conclude that it cannot be irreducible? Remember what you know about irreducible representation of rotation groups. And I'm talking about dimensionality.
Form an invariant combination like DI.
That's true, and that's what we will do. But I actually had in mind even something more simple. More simple is that we know that this for each I, this solution gives you 2L plus 1 dimensional representation. But and we know that these are dimensionalities of a reducible representation of rotations. But here it's multiplied by 3. So you have 3 times that. Therefore, there should be another constraint to get rid of it. And indeed, this another constraint is simply that the divergence of this thing is 0. We actually, and that demonstrates the general approach which you have to use with these wave equations, which is you have to eliminate as many things as possible, and you have to account for the what would be the fact that we transform it in a way which involves this vector index k. They are not. There is a difference between, say, 3 independent scalar fields and this vector field, because the transformation law mixes different components. In physical terms, what we call what's the name for this? When you have a field in which rotation acts on the components of the field. There is a simple physical term for this thing.
The vector potential.
The term is spin-orbit interaction, because you see, I is a spin index. You are describing things using, and in this case, spin is equal to 1, because we have 3 components. So we have the spin equal to 1. And when we rotate our equations, we assume that our equations are not on. You see, you can ask the question, okay, suppose I don't want this. Suppose I simply say that it transforms as independent, as 3 independent scalar field. What goes wrong in this case? What goes wrong is the following. Let's suppose we write down some effective action for this field. And the effective action which gives us a Laplacian for the scalar field is just this. When you vary it, you get the Laplacian, right? And it is obviously invariant under rotations. I'm sorry that I'm telling you these elementary things, but we will really need this understanding, clear understanding of these matters. Okay, and now give me an example of the effective action for the vector field. In one effective action will be invariant under simple transformation. So we have a possibility which I eventually eliminate. So what would be the effective action which is invariant under these transformations? Just somebody. Yes.
Just some.
Yeah. Let's simply take. It's clearly invariant under 3. You can treat the index k as a just. It just enumerates the fields, and that's it. Now, what would be? But that's not the actions we obtain. What would be in particle physics and in condensed matter physics? So what would be the action which will require us, excuse me, let me let me stress one more thing before we go to the next step in this action. Notice that the feature of this action is extended symmetry. What extended symmetry? It has not simply rotation symmetry, simple rotation, not simply O3, but what is the symmetry of this action?
O3 cross O3.
O3 cross O3, yes. Because you can rotate quite independently space and spin. If you call these indices spin, they are completely independent. Now, the true action which comes out, well, it will come out from the Ising model and many other things. It has only one O3. It doesn't have two O3s. So, what would be the action which requires simultaneous rotation of spin and orbit? What will be, how would you write a term in S which will break O3 cross O3 but retain O3?
Well, if we didn't have the di AI 0, we can write di AI squared.
Yeah, for instance, we can exactly, if you have di AI square, well, then with some arbitrary coefficients, we will actually have the symmetry, the symmetry on the single O3, because now you have to mix, you have a mixing of orbital. This partial I actually transforms as a vector under O3. So AI must transform. And I suggest you check yourself that when you substitute this and change variables, then indeed this will be the symmetry of this thing. And this is precisely what is called spin-orbit interaction. Orbit is represented by partial derivatives, spin is represented by the index. Now, all this is corresponds to spin 1. With spinors, it's basically the same. You have a spinor index alpha, and you have a spinor representation for the group G, psi beta of G, psi beta of X, and that's what leads to the Dirac equation. The Dirac equation, the Dirac action is psi gamma mu d mu psi. Gamma acts on spinor indices. Once again, it's invariant only under simultaneous transformations of spin and orbit, because d mu rotates when you change the orbits, and you have to add this term to compensate for it. Because if you don't touch spin and rotate orbit only, then gamma will be a scalar and d mu will be a vector. Okay, very good. Now,
There should be lambda x, right?
well, you see, I just want to lambda of gx. And lambda is the, well, I will know, you know this. That's a standard thing about spinors, which I don't want to go further into that. But I want to ask you a question. What do you think will be there is the analog of the spin-orbit symmetry? Okay, let me formulate it once again. So our conclusion is that we have rotation group first of all, and this rotation group acts both on spin. Spin is defined as an angular momentum in the rest frame, and therefore is just the represent, this is the spin coordinate, spin index. And so the rotation must act both on the spin index and on the orbit. And this is true for any representation. If you write down the most general action, of course, if for some reason this term is absent, then we have an extended symmetry or 3 cross O3. But that's not that's very rare. I can't even give you an example. This, by the way, the action as it is written is precisely what describes elasticity theory. It's a soft modes. It's the Landau energy for elasticity theory. Do you remember the name of the constants C1 and C2, of some combination of the constants C1 and C2? Sort of, yeah. It's Young. Actually, I forgot it myself. I think Young moduli or something else. Anyway, that's in this case AK is a displacement of the atom. And, so, okay, all this was just child play. Now a slightly more complicated question. What do you think about this expression? What kind of symmetries? And I claim there is a spin-orbit interaction and some symmetry here. It cannot be rotation symmetry because we're on a lattice. It will become rotation symmetry when we go.
Z4 symmetry?
Yeah, we have Z4, we have rotation by pi divided by 2. And you see that when you rotate by pi divided by 2, it's very important that the index A changes. So, in fact, you actually have to, you can check that when you rotate by pi divided by 2 and simultaneously change A plus 1, the equation doesn't change. You can check it. Let's put it as an exercise. And since it doesn't change, and by the way, we immediately see that the representation is double valued. When you rotate by 2 pi, this thing, we get the minus. And that's how this tail gives us the string gives us the a double valued spinor double valued representation, which represent identical rotation modulo sign. Here, everything, all these tricky things come out very naturally. You have very clear thing. And now it's, I will not, I'm already moving slower than I intended. So I will not do carefully this analysis. The only thing which I shall tell you, and which you can try yourself, is in order to make invariant decomposition of this equation, because this representation will still be reducible. However, you can write it down in the following way. Complex conjugate plus v plus e to the 3I pi divided by 2, and also plus complex conjugate. And the procedure should be to get the equations for u plus and u minus. Now, why I'm choosing this? I'm claiming there are only two terms, well, which is not surprising, because if there are 4 independent quantities, 2 u's and 2 v's. Here is Ci, and the question is why we use this decomposition, why it will be very, very, very useful. The answer is that it's just as when you have continuous rotation on a plane. Suppose you have continuous rotation, then the irreducible representation are simply, for continuous rotation, the functions e to the I and phi, where phi is the angle and n is the angular momentum, or I and alpha. That's for the full group of for full rotation group. But here we have a discrete rotation group, rotation by pi divided by 2. So there should be, let me say it again, when you have any rotational invariant expression, you can always split it onto irreducible components corresponding to fixed angular momentum n. And angular momentum goes from minus infinity to plus infinity when we're talking about rotation in 2 dimensions. And if we're talking about discrete rotations, and that's the origin, by the way, of Fourier decomposition. That's the Fourier decomposition. Any function of alpha is sum over n. Now, when you have discrete rotation, there should not be infinite number of these things. The number should correspond to the number of independent rotations. And here we see it. It's spin 1/2 and this spin 3/2 component. Anyway, after we're doing this, you get the usual Dirac. The interesting thing happens. These 2 terms separates in the continuous limit. This remains short-ranged while u becomes near the critical temperature. This equation reduces to the following. So, write it down. Yeah, go ahead.
So this rotation symmetry by pi over 2 is the rotation center, the dual lattice, or?
Well, you can start with the original lattice, and then rotate it over. Rotate simultaneously the dual lattice and the original lattice. So you rotate x with respect to this thing. Now, the final equation, which I probably should have started with, is just the Dirac equation, which can be written down in the following way. It's convenient to introduce complex variables, and we have and m is proportional to t minus t critical. So the main point was that we got this, due to this order disorder thing, we get linear equations. After that, it's a matter of standard technique to proceed. The really non-trivial, really miraculous fact is that this equation is linear for the order disorder. And as I will tell you, in 3 dimensions, it's also linear in the sense. So, but we still don't know how to solve it. In 2 dimensions, everything is simple, and that demonstrates, by the way, this talk about irreducible representations demonstrates the point of view that sometimes is convenient, that elementary particles should correspond, they are simply can be defined as irreducible representations of the full symmetry group. Here I talked about rotations. In space-time, I have the group of Lorentz transformations plus translations, 10-parameter group, which is called the Poincare group. So elementary particles can be defined as irreducible representations of the Poincare group. It's a limited view, but sometimes convenient, sometimes not. Still, it's worth keeping it in mind, because sometimes you better concentrate on this group theoretic structure and forget about everything else, not to be distracted. But sometimes this limited view is not enough. Okay. Yeah.
Why are we stopping at spin 3/2 here and not this?
Oh, very good. Because you see, if you take spin, say 5/2, okay, then it will be indistinguishable. If it is, of course, if you have continuous rotation, it's totally different thing, spin 5/2 and spin 3/2. But if you allow rotations by pi divided by 2 only, it will be the same exponential, it will be the same value. And that as it should be, because it is in continuous rotation, we're dealing with infinite number of rotations and infinite number of coefficients of spins. But here we have just 4 rotations. So it's just that for this discrete rotation, it stops here. For continuous rotations, it continues indefinitely. Okay. And now let's calculate. Let's now come to really maybe maybe I shall tell you one more thing, in spite of lack of time. I shall tell you about. I really feel I wanted to tell you this simple thing quickly. What about how the same picture of free fermion? We got free fermions from here, which are order-disorder parameters. From here, we will derive all anomalous dimensions, critical exponents, and so on. And it's the start of conformal. It's some very special and simple example of conformal field theory, but it will allow us to generalize. But let's take a geometrical view of this. Here I introduced disorder and fermions in a using algebraic approach, so to say. But let's do it geometrically. Remember, we have the partition function. So this is an alternative geometric approach, which we will only touch very lightly. We had the problem that when we have a we know that when we calculate in the Ising model, this diagram, I'm using low temperature expansion, and this diagram is coming with a coefficient 1, because when we it's just a drop with spin minus, and there's no special coefficient. When we looked at the Bose field, we have three diagrams instead. This one plus this one plus this one. These three so if we take simply free field phi without adding this log cosh, we get the coefficient 3, as I mentioned. Now, what happens when you have fermions? A very beautiful thing happens, actually. What happens is that this diagram will come with the sign plus. This diagram will come with the sign plus, and this diagram will come with the sign minus. I shall explain what kind of contours we get. We will get representation of the partition function as a sum over contours with a weight C. But they are fermionic contours, and that's an interesting notion, which is actually important not only in this problem. So that's why I'm, despite lack of time, I'm talking about it. I think that's worth knowing. Okay, so how to get the right coefficient? There's a very cute idea which is invented partly by Feynman, partly by Mark Katz, which is to notice that if you have an arbitrary contour, the change, and you apply, you introduce, let me do this. Let's suppose that on each contour you can draw the tangent. You see, if you have this contour, then the rotation of the tangent is equal to 2 pi when you go around the contour. If you have this thing, the rotation of the tangent is what? For the figure 8? Huh? 0. The general formula for this is delta phi is equal to delta phi divided by 2 pi is equal to nu plus 1 modulo 2, where nu is the number of self-intersections. Using this formula, you find out that if you sum over contour, I call it C, yes, C e to the minus mu L of C and e to the I delta phi, or I can write it down as phi dot ds. If I add this, I will call it the spin factor, I phi dot s. Then this factor will give me, so in other words, each part of the contour, each contour gets this term, and this is the partition function. And as a result, I will get the correct counting of this thing. You can find something about it in the Landau-Lifshitz book on statistical physics, and in Feynman's book on statistical mechanics. But in fact, in both cases, although these are great books, but it's somewhat overcomplicated. If someone gets interested, I will show you some very simple way to treat these things. Now, this term, and it's I divided by 2, it gives precisely the coefficients minus 1, which I needed for cancellation of wrong thing. And this is, on the other hand, it's a spin factor. It shows that when you rotate when trajectory rotates, there is spin-orbit interaction. This is just the example of spin-orbit interaction. And what's remarkable, there is a spin-orbit interaction like that and spin factors in 3 dimensions also. And they are useful in the case of quantum Hall effect and anyons and all other things, which maybe we will touch later. But the simplest origin of this spin factor is just this Ising model thing. Okay, now it's high time to proceed to the conclusions from this analysis. So far we get just some formal stuff. I can just announce you without really discussing that if you have 3-dimensional fermions, then there will be a similar factor in the exponential, in the sum over paths. However, it will be related, the 3-dimensional curves have what is called torsion. It's the way, it's how much they deviate from the planar curves. And what it turns out that what enters here is just this torsion. So you see, it's a nice and geometrical. And they describe some elementary excitations. That's just an alternative geometrical description of elementary excitation. Okay, now what are the conclusions which we draw from this analysis? First of all, we know that we understand that we get we have Majorana fermions, and the correlation function is of two Dirac fermions in 2 dimensions is very simple. It's 1 divided by x minus y. Where it's bad notation, it's complex numbers here. Now we want to calculate the energy density, which is the energy density is sigma x plus delta, sum over delta. And that's the energy density at the point x. And this is simply in the continuous limit when everything it's very easy to express in terms of the fermions, because the fermion is sigma x mu x plus delta, and you immediately see you can either take psi x, it will be mu psi x prime, the nearest neighbor, it will be the mu, or it will be the sigma. And of course the sigma is the same as mu mu, so the energy density is proportional to the bilinear of 2 fermions. These are the usual Dirac Majorana fermions which you get in any textbook on field theory. And the energy density is psi. So the correlation functions of 2 energy densities. What's the physical meaning of the correlation function of 2 energy densities? So it's a general question of statistical mechanics. You have e to the minus beta sum epsilon x. I will put the question differently. Sum over configurations. That's the Gibbs partition function. And suppose I'm interested in specific heat. How can I get, and that's also it's by definition e to the minus beta multiplied by f, where f is free energy. What should I do to get the specific heat of this system?
Calculate the variance.
Huh?
Calculate the variance of the energy.
The what?
The variance of the energy.
Fluctuations, yes. Actually, you have to differentiate it with respect to beta, and specific heat is just the sum over x of the correlation functions like that. When we plug it in there, we have the correlation function psi, 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 and that gives us 1 minus integral over d to x, integral over d to x, x squared. So what kind of conclusion we should make now? All this formula is of course correct for zero mass, because if mass is non-zero, you will have exponential suppression. So at zero mass, so now translate it onto the original language of the Ising model. What conclusion we are making?
So definitely divergent with respect.
Yeah, it means the following. Exactly. We have specific heat which depends on temperature. At the critical temperature, we get divergent integral, and of course it diverges as written. It diverges at small x and at large x. So which is meaningful, which is meaningless? What? Huh? Small x is meaningless as a trivial thing because we have a lattice, but the large x is very important. Namely, it means that the specific heat is T minus T critical. So it is, I will explain it a little better, but what is really important is that infrared divergences, these large-scale divergences, lead to singular thermodynamic quantities. And indeed, experimentally, when you measure specific heat of various systems, there are huge peaks at the critical temperature with various, in two-dimensional systems of the Ising type, it will always be the logarithm. In other systems, it will be, well, we will see what kind of possibilities we have. Even in 2 dimensions, it's not always the logarithm. There are many important systems in which it's different, but it's always singular. Let me see how we are doing with time. We are doing pretty poorly. Yes?
Should it be e to the I pi a over 4? Because you want psi a to transform this.
Oh, I think you are right. Wait a second. We need, yeah, sorry about that. We need that as a goes to 4, a plus 4 changes sign. You are quite right. And what I will tell you why I made this mistake. I made this mistake because I wanted rotation pi divided by 2, and it should be multiplied by the spin. And the mistake was related to the fact that I forgot that the spin is 1/2. So it is spin is 1/2 in this term, and spin is 3/2 in this term. And rotation is pi, so you multiply spin by the angle of rotation. Rotation is pi divided by 2, or 3 pi divided by 2. Okay, so we can also calculate using these free fermions other correlation functions. And it will be, tomorrow it will be our starting point for the general conformal field theory. It's just, you see, you try to see in the exact solution some seeds of much more general and comprehensive theory. And they are indeed there. So the other result, which I actually quoted already, is that if you have a correlation function of two spins, then it behaves like 1 over x to the power 1/4. And try to remember, at some point I mentioned not literally this result, but closely related thing. When we looked at the Dyson equation and corrections, I said that the self-energy part is much greater than the, so to say, original Baire propagator. This is the Baire propagator. This is the interaction, which contains all Feynman diagrams. And I was saying that this is irrelevant in comparison to this. And for that, I quoted the answer for G minus 1. What was the answer? Actually, it was just the Fourier transform of this guy. If you go to K representation from here, you get K to the 7/4. And that leads to this extremely important idea that actually I can in the last minute tell you what we will be doing tomorrow. So we drop the Baire propagator. After that, all kind of Feynman diagrams, they become scale invariant because the scale is some memory of the scale is contained here. So if this is negligible, then the result should become scale invariant. And moreover, it will be not only scale invariant, but conformally invariant. And that we will see tomorrow. But the key, a very important thing to remember, that in all equations of, for example, when you have, this is the green function, if you have some 3-point function like that, again, usually as in QED, you have Baire term plus something like that. And the idea will be that this is again negligible and all the rest is conformally invariant. Okay, let's stop here.